Hello and welcome to another lecture of Advanced Fluid Mechanics. I am Salman Zaidi, lecturer in the Department of Civil Engineering at University of Goa. In today's lecture, we will work on problem 3, which involves the application of energy equation to determine the required head of water flow in the pipeline system. Uh, the problem deals with water flowing at 80 degrees Fahrenheit from a storage tank through 550 feet flowing feet of 6-inch schedule 45. Uh, as you can see in the problem, our task is to calculate the head loss above the pipe inlet that is necessary to produce a volumetric flow rate of 2.50 feet cube per second, taking into the account the kinetic energy due to the pipe friction. This problem is particularly important because it highlights how theoretical principles of fluid mechanics, such as Bernoulli's equation, head loss due to friction, and Darcy-Weisbach relation, are applied in real-world engineering systems like water supply, pumping, and distribution networks. Let's move to the problem. Um, Here you can see that we have the storage tank and the pipe is connected to it. And the diameter of the pipe is 6-inch schedule 40 pipe and the length of the pipe is 550 feet. And we have the height of water as h. This is the equation, which is Bernoulli equation. We have the pressure head, elevation head, and kinetic head or velocity head. Additionally, we have the value of head loss, which is going to be lost during the traveling of water from top surface of the tank towards the outflow point. So, as we know, at point 1 lies at the surface of the tank. So we have the pressure P1 at here, which will be equals to 0. And so as so on, we have the velocity, which is also 0, which is denoted as V1 at the surface of the tank equals to 0. So these both terms will be cancelled as P1 over gamma equals to 0 and V1 over 2G equals to 0. So at point 2, which is lies outside the pipe, over here, so P2 will also be equals to 0 because there is no pressure other than the atmospheric pressure acting on the pipe. So P2 term will also be equals to 0. So now modify the equation according to the values. Let's see what we have got here. We have head loss, which is at the left-hand side of the equation, and all other values like elevation Z1 minus Z2 um, and velocity head also on the right side of the equation. So let's modify the equation. We have this equation H or head loss equals to Z1 minus Z2, which will also be equals to HL plus V square over 2G. Let's move towards the second step of the problem. Uh, as we can see from the question statement, we have schedule 45 and have a diameter of 6 inches. So what we need to do is to uh, take the and other all other dimensions. We can see that are in feet. So we need to take convert the schedule 45 into inches, and its inner diameter can be calculated or can be taken from the appendix, and also its area is also available in the appendix. So let's move towards the appendix. I will Just show you appendix. Have here. So this is the appendix. We have all the values for the water as the flowing fluid is water. So we have the table of water from temperature 0 to 100 in degree centigrade, also in the Fahrenheit. So from appendix A to we have the value in degree Fahrenheit, and basically US customary system we have all the values like specific wear density, dynamic viscosity and kinematic viscosity. So let's move uh, on to the main lecture. So for the schedule 46-inch pipe, we have the area equals to 0.2006 and diameter equals to d 0.5054 feet. So you can see from the table H, sorry, F, which is the schedule 45, our diameter of the pipe was 6 inches and its inner diameter is 6.056 inches, and we have the inner area of that pipe equals to 0.2006. So we have the areas and diameter from the appendix H. We have written here all these values. Now let's move towards the second phase, which is calculation of Reynolds number. And for that purpose, we have the diameter, we have the kinematic viscosity from the appendix A2, but we do not have the value of velocity. So to calculate the value of velocity, we need to um, divide discharge with the area of the pipe. So the discharge equals 2.50 and area we get from the appendix H uh, 0.2006. So we have the velocity value 12.46 feet per second. So let's put this value into Reynolds number equation, and we have the value of Reynolds number equals to 6.88 into 10 raised power 5. So if you want to see the value of kinematic viscosity, we have that value in the appendix. Here is the value of water at 80 degree Fahrenheit. Uh, you can see that 9.15 into 10 raised power uh, minus 9. So let's move towards the question. Okay. So the other thing we need to be notice that uh, what type of pipe we are using. It's schedule 40 steel pipe. So for that steel pipe, we need to note down the value of roughness, which is related to the pipe surface. So the value of roughness is 1.5 into 10 raised power minus 4 feet. So that is the another value that will be required from the table. So let's move towards the table. We have the value of different values of roughness in the table. So let's take the value. Let's see where we have. This is a steel pipe, and we have the value of steel equals to 1.54 into 10 is power minus 4. So let's pick the value for the roughness, and now move towards the main equation, which is related to the friction factor. So what we have is the ratio of diameter of the pipe and the roughness, that is called relative roughness. Value of relative roughness equals to 3369. So let's find out the value of friction factor F, which can be calculated from the value of D over E, which is the relative roughness, and the value of Reynolds number. So what we need to do is to write down the both values on the Modi diagram and calculate the value of friction factor F. Okay, so let's move towards the friction factor and Reynolds number value at the Modi diagram. 6.88 into 10 is power 5 is the Reynolds number value, and the value of D over E is 3369. So from the Moody chart, we can determine the value of friction factor. So here's the Moody diagram. Uh, at the y-axis, we have the value of D over E, which is about 3369. That lies over here. And the value of Reynolds number was like 10 raised power 5. So the values was about, you can see that we have the value of Reynolds number 6.88 into 10 raised power 5. So what we need is to see here 6.88 into 10 raised power 5 like here. So at the x-axis, 6.8 is lies between 6 and 8, and here's the 7. So just before the this line, we have the value of Reynolds number. Let's uh, extend this line and check out the point where about the value of relative roughness D over E collides with that point, and then extend these lines to in this direction of friction factor. So that's how you calculate the value of friction factor by using Moody diagram. So what we have got is the value of friction factor F, which is 0.016, slightly above the value 0.015. So this is the friction factor. And let's put the value of friction factor in the main Darcy equation. Um, we have the value of F equals to 0.0165. The length of the pipe was 550 feet. So let's put the value of that in the equation. So 550 here, and then diameter of the pipe, and then velocity was calculated as 12.46. The value of gravitational acceleration G is 32.2 feet per second in the feet scale per second in the Darcy equation, plus again we need to put the value of velocity and G in that equation. So the head required for between point A to point B is what is 45.7 feet. So that's how uh, we can calculate the value of head above any 2 points by using Darcy equation and the concept of relative roughness and Moody diagram. That that's all about the problem number 3. So we will discuss the other problem related to pressure distribution in the next lecture. Thank you. Let's move to the problem number 4, which is related to the again the pressure difference. We need to find out the pressure at point A. Uh, from the figure, we can see that we have the overhead water storage tank, which is connected with the pipe from point A to point B. The top of the tank is over here, and we have the height of the water and storage in the tank is 1.5 meters. And from the bottom of the tank towards the center line of that pipe, we have the height equals to 7.5. The pipe we have used in that connection is type K copper tube pipe, which needs to be noted down so that we will use the value of the pipe material um, in a coming lecture. So the diameter of the pipe was 4-inch square pipe, and its uh, the length of the pipe is 70 feet straight, and then we have some vertical parts of the pipe as well. So the elevation difference of the point A lies over here, and the point B lies at the bottom of the pipe is about 12 meters. So that's all about the question. Let's move towards the answer. But before moving towards the answer, we need to discuss the question. The fluid that is flowing through the point through this pipe is water at 10 degree centigrades, and the discharge of the through the pipe is 900 liters per minute. That will be converted in meter cube per second after that, and through the pipe as shown in the figure, we need to compute the pressure at point B, considering the energy loss, which is also called as head loss due to friction, but we need to neglect other losses as well. So let's move towards the solution of this question. We will need to use the Bernoulli's equation, which is again the addition of pressure head, elevation head, velocity head, and the head loss will be uh, neglected or can be minus from this equation. We need to find out the pressure at point B. So we will rearrange the equation and multiply the all the denominators value, like cross multiply with the equation, and the remaining required pressure B will be calculated and will be taken at uh, most left side of the equation. The other values will remain same. So what we have gamma W that will be cross multiply with this that equation. So the equation becomes this. But moving towards this part of the equation, we need to see that at the point one lies at the surface of the tank. So the pressure at point one or point A will be equals to 0, and so as the velocity at point one will be equal to 0, and the discharge need to be converted as it is given in 900 liters per minute. So we know that 1 meter cube equals to 1 meter cube per second discharge equals to 1000 liter. So what we need when we need to divide 900 liters with 1000, and as this is given in minutes, so we need to convert it into seconds. So we will multiply 1000 with 60, and then the answer will become 0.015 meter cube per second. That is converted from liter per minute to meter cube per seconds. So now we can calculate the value of velocity, which is equals to Q over A. So the value of velocity equals to 1.99 meter per second. Let's put this value into the main equation, which is related to the Reynolds number. And as we know that Reynolds number and d over E will be used to find the value of friction factor, which is the main parameter to find out the head loss, which will be used in this equation. So how we can find the value of friction factor? We already discussed that in this previous problem.
we have the value of Reynolds number and the our E value. Reynolds number value can be calculated by multiplying the velocity, which is already calculated, and the diameter of the pipe, which is we know that the 4-inch type K copper tube pipe, or for that purpose, we have the appendix F and appendix H. For copper tubing, copper piping, we have appendix H. So the diameter was 4 inches. So we will see that row for the flow area. We have the 8.114 into 10 is power minus 2, and the inside diameter equals to 97.997. So we will use these diameters and the areas value uh, for that equation. So uh, So we have diameter 0.0998 from the appendix H, and the area we have used is this from the table. So the value of D over E can be calculated, and the value of Reynolds number um, can be calculated by putting the value of kinematic viscosity, which is at 10 degrees centigrade, water have the kinematic viscosity equals to 1.30 into 10 raised power minus 6. So we have this table A1 at 10 degrees centigrade. We have the value of 1.30 into 10 raised power minus 6. So this is the value we have chosen from the table. Okay. So let's move towards the last part of the question. We have the Headloss equation, which is the Darcy equation, and we have the value of f, we have the value of length of pipe. So length of the pipe is the major concern to calculate. So we have the value of straight pipe, which is equal to 70 feet. We have the value of a vertical pipe, this one, which is 7.5 meter long. So we have the total value 770 plus 7.5 equals to 77.5. Also, we need to find out this vertical pipe height. So how do we calculate that? We just simply uh, take this value, which is 12 meters, and then subtract this value 12, um, 7.5 meter, and 1.5 equals to 9 meters. So what will be the height of this pipe? 12 minus 9. This is the combination of 7.5 and 1.5 equals to 9. So 12 minus 9 equals to 3 meters. So the value of this vertical pipe equals to 3 meters. So the total value of that pipe will be equal to 70 plus 373, and plus 7.5 equals to 80.5. So that's how we have the value of pipe equals to 80.5 meters. So let's put other values, which is diameter and G 9.81 we will use in that case, and the value of velocity. So the head loss will be equals to 2.735 meters. So now we have the head loss value. We have the elevation difference, which is 12 meter from point 1 to point B. So we will put that into that equation. So we have the velocity value v square over 2g, g equals to 9.81, and the we have the last value, which is equals to head loss. So head loss equals to 2.735, which we have calculated from the equation of Darcy. So we have the value of pressure at point B equals to 89.9 kilopascal. So that's how you can calculate the value of pressure at any point between any pipeline and the tank. That's all from the today's lecture. Thank you for your interest. Allah Hafiz.